In this video we're going to look at circle theorems, but before we do we want to consider the different parts of a circle. So what we have is that this curved part of a circle is called an arc, and the triangular shape which is beneath the arc, this is called a sector. This dashed line, which extends from the centre of the circle to the circumference, is called a radius. The line that extends from one side of the circle to the other, which passes through the middle, is the diameter. The part of the circle that goes all the way around the outside is called the circumference. This line, which is similar to the diameter, only it doesn't go through the centre, so it goes from one side of the circle to the other without passing through the centre, it's called a chord. So really the diameter is also a chord, but it's a very special chord because it goes through the middle. This part of the circle that's beneath the chord is called a segment. And the line which just touches the circle at one point is called a tangent. Now again, these next couple of things are very useful, but they're not circle theorems. So we should be familiar with the fact that angles in a quadrilateral add up to 360 degrees. If this angle is 90 and the bottom angle is 90, that means they add up to 180, which means the other two angles add up to 180. So if this is 50, the missing angle at the corner is 130 degrees. Also then, if we have a circle and we've got two radii that are drawn, they are a constant length. And what we should do is to put the dashed line or the line in the middle of them, denoting that they're the same length. Because then if we have to draw a chord between those, then what it'll remind us is that we've got an isosceles triangle, or there could be other uses as well. Subtended angles. So we're going to look at a few examples of what the angles being subtended by the chord really means. So the first thing we're going to do is draw a chord AB on the first three, and I'm going to draw a diameter on the last one. So the first one, the angle subtended by the major segment by chord AB, that's going to be an angle in the top part of the triangle, or the circle, because we're in the major segment. So that's talking about the angle at the top. The next one then, we've got the angle subtended in the minor segment. So the minor segment is the smaller segment. So it's the one beneath the chord in this case. And that's the angle in here. The angle subtended in the centre. So we're going to mark on the centre and we'll draw our angle so that it's subtended at the centre. That's going to be the angle formed up to the middle. So that's our angle here. And the angle subtended by the diameter, it could be in either segment there. And it doesn't matter which, because we'll find out later, but they are the same length and the same size. So that's the angle theta. Our first theorem then is talking about the angle at the centre of the circle. And it says that the angle at the centre of a circle is twice the angle at the circumference when they are subtended by the same 2 points. So the angle at the centre is 2p, then the angle at the circumference is going to be p. And the Star Trek logo looks like this triangle, so you may want to consider it to be the Star Trek rule. One thing we need to watch out for is the angle subtended in the minor segment. So again, we've got the points A and B, and this the point P here, this is going to be the angle in the minor segment. Then the corresponding angle at the center is the obtuse angle here, or the reflex angle, so 2P. So we need to be careful with that. So it still applies. So the angle at the middle is still twice the angle at the circumference. And the second theorem, the angles in the same segment. So here we've got the 2 points A and B, and these two angles are in the same segment. So they're in the major segment. And angles from the circumference in the same segment, subtended by the same 2 points, are equal. So these two angles are P. And what we could think about that is a butterfly, because we all know that butterflies' wings are symmetrical. And the same idea here, although the wings in this case are different sizes, it's still the same idea. So the angles at the top are equal. And we can actually extend this further. And we could have all of the angles drawn in the same segment. Well, this is also P. And this angle will also be P. So all the angles that are subtended by the same 2 points that are in the same segment are equal. And we can do this for the minor segment as well. So the angles here, let's call them Q, they're all going to be the same size as well, because they're subtended by the same 2 points and they're in the same segment. So example 1, find the named angles giving reasons for each. So example A, find the angle PRS. So what we have in this case is that angle Q and R is going to be equal to each other. They're going to be equal to each other because they are in the same segment and subtended by AB, or PS, sorry, in this case. So angle R, or PRS, is going to equal 85 degrees. And that's the other way to think about that is it's the butterfly rule. Example B, we want to find angle YXZ. So that's this angle at the top, and also angle YTZ, and that's the angle here. So what we've got is that the angle at the middle, so the angle subtended by YZ at the center of the circle is 90 degrees. So we've got 90 degrees here. So that means the angle YXZ is going to be 45 degrees. So YXZ is 45 degrees. This is the Star Trek rule, where the angle at the middle is twice the angle at the circumference. For angle T, then, we can apply the same principle, only in the minor segment. So if we consider the reflex angle outside of O, it's going to be 270 degrees, because the angles at a point add to 360. So 90 plus 270 equals 360. And then the angle at the center is twice the angle at the circumference. So that means that YTZ is going to be 135 degrees. And that's half of 270 degrees. Again, Star Trek. Or it could be the more formal language would be the angle at the center is twice the angle at the circumference. In example C, we want to find angle ACD and ADC, which is this full angle at the bottom. So what we have first of all is angle ACD is going to equal 30 degrees, and that's because angle C and angle B are subtended from the same points. and they're in the same segment. And that's the butterfly rule. And we can see that it's a butterfly if we consider it here. So we've highlighted the two parts of the two wings of the butterfly, so the angles at the top should be equal to each other. Then to work out the angle at D, well, what we have is a triangle, ACD, and we know the angles in a triangle add to 180 degrees. So we've got 25 plus 30 plus ADC must equal 180 degrees because of the angles in a triangle. So that means that ADC is going to be 180 minus 25 minus 30, which is 125 degrees. Our third theorem then deals with angles in a semicircle, and the angle subtended by the diameter is 90 degrees. So the angle, we've got the diameter AB, which passes through the centre C, and the angles at the circumference are all 90 degrees. The reason for this is that it's a special case of theorem 1. So theorem 1 we know is the Star Trek rule. So the angle at the middle, if that's 2p, the angle at circumference is p. So if we were to move these 2 points around the circumference to the ends of this triangle, that would make the angle at the middle equal 180 degrees. And then the angle at the circumference is going to be half of that, which is 90 degrees, which is a right angle. And that's going to be the same in either segment. Theorem 4, and the last of the circle theorems to do with angles within the circle. The opposite angles of a cyclic quadrilateral add up to 180 degrees. And a cyclic quadrilateral is any quadrilateral that's contained within a circle where all 4 vertices lie in the circumference. So if we were to just draw a quick circumference or quadrilateral ABCD, then that's not a cyclic quadrilateral because point D is not on the circumference. So the angles on the opposite sides, they are not equal, but they add to 180 degrees. So that's a common mistake. So people would say that P and R are equal to each other and S and Q equal each other. And it might look that S and Q are very similar. So the confusion there is okay to understand. You can see where that's coming from. But P and R, we can see in this case P is an acute angle and R is an obtuse angle. So clearly they can't be equal. So the relationship between the opposite angles of a cyclic quadrilateral, so a quadrilateral where all 4 sides, 4 points are on the circumference, they add to 180 degrees. So example 2, find the named angles, giving reasons for each. So number 1, angle PSR. So that's the angle at the top. What we have is that angle S plus angle Q must add together to give 180 degrees because PQRS is a cyclic quadrilateral. So then S is going to be 180 degrees minus 95 degrees, which is 85 degrees. Example 2, find the angle XYZ. So to do that, what we can notice is that XYZ is a triangle and we have one side. So if we could work out the angle X, then we could work out Y. And angle X, or ZXY, that equals 90 degrees because angles in a semicircle are 90 degrees. So then we've got 90 plus 25 plus y must equal 180 degrees because the angle's in a triangle. So that means that y is going to be 180 minus 90 minus 25, which is 65 degrees. And example 3, find the angles ADC, which is this full angle down at the bottom, and then angle ACD, which is this angle in red. So to work out ADC, what we have is that ABCD is a cyclic quadrilateral. So opposite angles add to 180 degrees. So that means that B plus D must equal 180 degrees. The full angle at B is 60 degrees. So D must equal 120 degrees. Then to work out angle C, what we have is that angle C is subtended by the points A and D, as is the angle at B. So that means that ABC is equal to ACD because they're in the same segment and subtended by A and D. So that means that ACD equals 40 degrees, or the butterfly would be another reason why that is true. And I've just highlighted the butterfly there, the wings of the butterfly, that we can see. So angle at B is the same as the angle at C.